In astrophysics and physical cosmology, Olbers paradox, named after the German astronomer Heinrich Wilhelm Olbers (1758–1840) and also called the dark night sky paradox, is the argument that the darkness of the night sky conflicts with the assumption of an infinite and eternal static universe. The darkness of the night sky is one of the pieces of evidence for a dynamic universe, such as the Big Bang model. If the universe is static, homogeneous at a large scale, and populated by an infinite number of stars, any sightline from Earth must end at the very bright surface of a star, so the night sky should be completely bright. This contradicts the observed darkness of the night. The paradox is that a static, infinitely old universe with an infinite number of stars distributed in an infinitely large space would be bright rather than dark. To show this, we divide the universe into a series of concentric shells, 1 light-year thick. A certain number of stars will be in the shell 1 billion to 1 billion and 1 light-years away. If the universe is homogeneous at a large scale, then there would be 4 times as many stars in a second shell, which is between 2 billion and 2 billion and 1 light-years away. However, the second shell is twice as far away, so each star in it would appear 1/4 as bright as the stars in the first shell. Thus the total light received from the second shell is the same as the total light received from the first shell. Thus each shell of a given thickness will produce the same net amount of light regardless of how far away it is. That is, the light of each shell adds to the total amount. Thus the more shells, the more light. And with infinitely many shells, there would be a bright night sky. While dark clouds could obstruct the light, these clouds would heat up, until they were as hot as the stars, and then radiate the same amount of light. Kepler saw this as an argument for a finite observable universe, or at least for a finite number of stars. In general relativity theory, it is still possible for the paradox to hold in a finite universe, though the sky would not be infinitely bright. Every point in the sky would still be like the surface of a star. The poet Edgar Allan Poe suggested that the finite size of the observable universe resolves the apparent paradox. More specifically, because the universe is finitely old and the speed of light is finite, only finitely many stars can be observed within a given volume of space visible from Earth, although the whole universe can be infinite in space. The density of stars within this finite volume is sufficiently low that any line of sight from Earth is unlikely to reach a star. However, the Big Bang theory introduces a new paradox. It states that the sky was much brighter in the past, especially at the end of the recombination era, when it first became transparent. All points of the local sky at that era were comparable in brightness to the surface of the Sun, due to the high temperature of the universe in that era. And most light rays will terminate not in a star, but in the relic of the Big Bang. This paradox is explained by the fact that the Big Bang theory also involves the expansion of space, which can cause the energy of emitted light to be reduced via redshift. More specifically, the extreme levels of radiation from the Big Bang have been redshifted to microwave wavelengths, 1100 times the length of its original wavelength, as a result of the cosmic expansion, and thus forms the cosmic microwave background radiation. This explains the relatively low light densities present in most of our sky despite the assumed bright nature of the Big Bang. The redshift also affects light from distant stars and quasars, but the diminution is minor, since the most distant galaxies and quasars have redshifts of only around 5 to 8.6.